sharing slides. Okay, do you see?
Yes, but not full screen yet.
Okay. Sorry. Okay, I have to. Are you seeing the full screen mode?
No. Yeah, now we see full screen mode, and we do see your mouse, so it seems to be okay. Go ahead.
Okay, thank you. I'm so grateful to the IAC members because of giving me this opportunity to talk about our recent work. And I am so grateful to the Masood because of his much efforts and attempts to handle and organize this workshop. What I'm going to talk is about the criticality of the hydrodynamic expansion, a collaborative work with Muhammad from IPM and Hassan from the Jagiellonian University. To this purpose, first of all, I am telling something about the motivation and why we are interested to this problem. And then I'll discussing some about the phase transition from general point of view to the young students. And afterwards, I would like to tell about the relativity hydrodynamics near the critical points and why it's important to modify or something we should look from another point of view to the relativistic hydrodynamics near the critical points. And specifically to quantify our model, we take the one-hour charged black hole as a dual model, strongly coupled field theory, which comes from the string theory construction. It has nice properties. For example, it has second order phase transition in a points of its parameter space. We use that model to study the hydrodynamics of a specific strongly interacting model which has second order phase transition, and we also look for the quasi-normal modes of this model, and from that computation we derive the critical momenta, the momenta which Andre had described, which is necessary to derive the radius of convergence of the hydrodynamic expansion. And finally, I'll discuss about the critical exponent in this model. Okay. Most of this workshop talks, almost 90% of the talks, are devoted to the mu b equal to 0 axis of the QCD phase diagram, where the nowadays colliders are working on it. And as opposed to this case, many less things are known about the physics of the depths of the QCD phase diagram. I mean, in this region where the future colliders such as FAIR and NICA are developing to study and probe the physics of this region, and also other models or other observations such as data coming from the neutron star mergers can give us reliable information about the equation of a state of the QCD or other things such as relativity hydrodynamics. How can it work in this region or not? And my today talk is about the hydrodynamic focused on this region of the phase space on the QCD phase diagram. For the young students, I have to say that, as you know, many different matters under extreme conditions experience lots of phase transitions, such as solid to liquid or liquid to gas phase transitions. And quantitatively, we can parameterize this phase transition by the behavior of free energy in terms of the symmetry breaking order parameters. For example, first order phase transitions are those that thermodynamic quantities such as entropy, pressure, energy, and so on are singular at the critical point, as you see in the left figure. And from the free energy point of view, you see that, for example, on this magenta line, you see the two phases which minimizes the free energy and have equal value for the free energy. And we can see that, okay, in this temperature, we have the system lives in a mixture of these two phases. But the second order phase transition are those that, as it calls, the second derivatives of the free energy are singular at the critical point. For example, as you see in the left figure, specific heat or susceptibilities are singular at the critical point, but the thermodynamic quantities such as entropy have smooth behavior just right on the critical temperature. And for the free energy, we have a smooth transition from the symmetry breaking to the symmetry restored phase. And I would like to say that this kind of transitions are classified by some critical exponent or critical numbers. But the main issue is that what's the relativistic hydrodynamic near the critical point? Since the hydrodynamic is a kind of dynamic model, we can no longer use the usual statistical mechanic. As you know, in the usual statistical mechanic, we have some kinds of critical exponent which classify the approach of quantities towards the critical point, like alpha, beta, or gamma, or other kinds of scaling relations. But when you consider the dynamical systems, it's not enough to just looking for the one-point function. By one-point function, I mean the energy, pressure, or so on. But you have to regard the quantities which encodes the information of evolution or dynamics of the system. For example, relaxation times or transport coefficients. And these kinds of functions, like as the static exponent, have some critical numbers. And for dynamical system, you have to consider these two numbers simultaneously. And I would like to say another things about the relativistic hydrodynamic, as Misha highlighted that, and I would like to emphasize it again. And it is that near the critical points, the validity of gradient expansion losses because of mixing the local time needed to relax the inhomogeneity, and it becomes the same order as the global time near the critical point because of drawing the correlation lens. And the consequence of this saying is that orders in the hydrodynamics expansion become the same, and this needs to include the fluctuation dynamics into the relativistic hydrodynamics equation. And this is again reiterations of Andre words about the radius of convergence for the hydrodynamic series. It's that the hydrodynamic, beside being close to the critical points or not, it's the asymptotic series, it is a divergent series. And to look for the radius of convergence of the series, we have to explore the nearest critical point of the spectral curve. And at the critical point, by the critical point, I mean the where which series stop to converge. And the benefit of a new paradigm of analytical continuations of the momentum to the complex plane. And practically, when we are using the computations just right at the critical point, We have we have an event that modes as if lie on top of each other because of these conditions which Andre had clearly described it. Since near the critical point, we have very strong regime and perturbation methods fail to work. We exploit the fluid gravity correspondence, which is an extension of the ADS-CFT conjecture. If I want to be short in this slide, I have to say that ADS-CFT is a kind of correspondence between some special solutions of supergravity with some theories on the boundary. In the large tooth coupling limit, as you see, for example, the bulk field can be sourced to the gauge invariant operator on the boundary side, and we can extend it to incorporate hydrodynamic perturbation, for example, on the boundary side, and it couples to the gravity perturbation on the bulk side. Our model, as I've told you, is a string theory construction, top-down string theory construction, which I'm by these words I mean that it has good compactification from string theory, type to be supergravity string theory to the lower dimensions, and on the boundary it relates to and strongly coupled inequal to for super Young-Mills theory, which has a finite temperature and finite chemical potential. The advantage of this model is that it has analytical solutions and it makes easy our job to study the hydrodynamics. And you see here the bulk action as well as the Gibbon sucking and the counterterm actions which are necessary to regulate and fix the bad behaviors on the boundary side. The history of phase transition in the gauge gravity models back to the early 80s, where Hawking and Page discovered that, for example, for asymptotically ADS-Schwarzschild geometries, there is a minimum temperature which below this minimum temperature, you have no any stable black hole geometries, you have just thermal gas, but above this minimum temperature, you have two solutions for the Einstein equations, and this is the first order phase transition, as I told you before. And we in a string theory construction, we have other phase transitions from bottom up or from top down scenarios. But in the one-hour charged black hole, a second order phase transition occurs at the y equals 0 point. As you see here, the determinant of this matrices, as I demonstrated to you, is singular on the y equals 0 point, and it is nothing but the second order phase transition. Why? Because these quantities represent the second order phase, second derivatives of the free energy with respect to the fields, the thermodynamic fields. I mean.
Farid, you have 10 more minutes for your talk.
Okay, thank you. Thank you. If I want to go some through the details of our calculations, the normal procedure is that you can take the gravity, gauge, and scalar fields and perturb them according to the diffeomorphism and gauge transformations and classify them on the little SO2 group. This is the normal procedure to solve the Einstein equation perturbatively. But we benefit of an alternative method, which is the master equation formulas, and it is that by rearranging the gauge field and gravity perturbations, it can work to form the Einstein equations to be decoupled into single master equations, and it also speeds up the quasi-normal mode computation. And retarded Green's functions are of great importance in the hydrodynamics since it can give us valuable information either about the transports of our model or for the excitations of the excitations of our theory. And in the ADS-CFD, it has a nice recipe. You have to follow these 3 items. First, solve linearized equations of motion for bulk perturbation fields with appropriate boundary conditions. And then you have to make unshell the total actions for perturbations, and it just left the surface term in terms of the currents, which are nothing but the boundary value of the bulk fields. And if you take the second derivatives of the unshell action with respect to these sources, you get the retarded Green's function, and that gives you all the information about the hydrodynamics of the strongly interacting model on the boundary side. Okay, as I've told you, for example, in the spin 2 sector, I'm showing you the computations. You have to first perturb the Einstein equations, for example, in the XY channel. This is very subtle equation to solve. We solve it perturbatively in small frequency limit. We get these solutions. We have these solutions up to the 3rd order in epsilon expansion. And by deriving the total action, I mean by combining also the bulk, Gibbons, Hawking, and the counter-term action, we get this formula, and we equate this total actions after taking twice derivatives with respect to the sources. We get this pocket formula for the transport coefficient, and in all the range of the parameter space, we get the ratio eta over S, the famous number 1/4 pi. And this result, I have to say that it's not new. It was derived in the Gobser paper almost 10 years ago. And in the spin 1 sector, we do the same calculations, and we solve for the plus channel, because this channel gives us the hydromodes. And the interesting result is that once you put this square root to be 0, then you get the critical momentum, which 2 equations become the same. And as you see, the critical momentum is derived from the equilibrium values of energy density, pressure, and density, number density of charged particles. And also we derive the hydromodes in this channel by solving the spectral curves in the small frequency limit, and we equate this perturbation with the corresponding results in the hydrodynamic expansion. We derive the θ1 transfer coefficient in the 3rd order conformal hydrodynamics. And as you pointed out here, it vanishes just right on the critical point, and we conjecture that it might be a hint of symmetry enhancement near the critical point.
5 minutes.
Thank you. And for numerical computations, for someone who are not familiar in this topic, I have to say that quasi-normal modes are poles of the retarded Green function, and it can give us the whole spectrum of the theory, not just the hydrodynamic modes of the theory. By solving the equations numerically, you are able to derive all the modes of the theory. And we use the pseudospectral Chebyshev discretization along the radial coordinates in the addiction parameterization, because in this coordinate, the Einstein equations are first order in the moment, are first order in the frequency, and it is very useful to solve it numerically. And the pattern of modes are very intuitive, are very interesting. As you see, for example, before the touching the critical momenta, modes move around and have nothing to do with each other. But after passing the critical momenta, they become the same. For example, by starting from one point in this complex plane and making a rotation 2 pi, for example, you are going around many families of modes. For example, in this case, you are touching 4 family of the modes in the spin 2 sector. And this pattern holds like in all range of parameters space, and in the spin 1 sector, the story is the same, but because of the mixing of metric and gauge perturbations, the game is very challenging and very interesting. Before that, I would like to comment about this diagram, which I think that one of our main results in this paper. The red dotted points represent the numerical values of the critical momenta, and the green lines demonstrates the values derived from the analytical solutions, and as you see, they coincide exactly with each other. And uh, for the whole range of the parameter space, as I've described, there is an interesting contest between the metric and gauge perturbations. For example, if you are seeing here the y equals to 0.8, which the critical momenta are defined by touching the first non-hydro modes of gauge and gravity perturbations on this point. But as you vary the y parameters to probe all the space of mu and t plane, you see different kinds of level crossing and collision between the hydro mode, which I don't have time to go further into them. And I jump to my last slide. To derive the critical exponent from these dynamical quantities, we make an expansion around y equals 0, which is the uh, the point at which we have phase transition, and many quantities are expanded around this point, and all of them are being like this. For example, as you see, the power of y is 1, and we conclude that the critical exponent in this model is 1/2, as it would be, and it is suggested by some other papers in literature. And to conclude myself, I have to say that we study the hydrodynamics of the strongly coupled field theory, which has second order phase transition, and by using the gauge gravity uh, busyness, we are able to study the hydrodynamics of this model up to the third order. In the gradient expansion, we derive the transport coefficient as well as the radius of convergence analytically and numerically. And to the future, we are planning to studying more carefully the relativistic hydrodynamic near the critical points by many general arguments, and also we are working in the low energy limit, which is the workplace for the, for example, neutron star mergers and something like this. Thank you.
Thank you very much for this interesting talk. We are a little bit over time, but we can still have 2 or 3 questions. Any questions? Andre.
Yes, thank you. Could you just, I didn't quite understand what kind of phase transition, so what kind of theory are we talking about, right? I mean, what is this phase transition? What exactly is happening? And
by the phase transition, you mean on the boundary side of which theory we take, or?
Yes, well, you are considering the dual of a certain theory, right? So you said it's top down.
Okay, as I told you, it is the n equal to 4 by having finite chemical potential, and it has also finite temperature.
So it's n equals 4 in 3 + 1 dimensional flat space, right? So
yes,
it's
yes.
And there is chemical. So there are 3 chemical potentials in general, right? So right. I mean,
no, we take 1 chemical potential. This is the gauge field is U1. We take
yes, but I mean, this is our charge chemical potential, right?
Yes, our charge.
Right. So are you taking the one which is diagonal, because there are 3 in general, right? So this is group SU4.
That's correct. We take that one which is diagonal.
I'm kind of okay. Yeah, I'm sorry. I still have to. Yeah, I promised to read your paper a long time ago, right? But because I am not quite sure what kind of transition you might have there of the second order, right? So that is a bit. But okay, I will.
By second order, by second order, I mean that the determinant is singular on the y equals 0 point.
You mean the Hessian, right? So there is a yes. So there is a point. Yes, I'm sorry. Yes, okay. So it's not. I mean, I think it's too quick to call it a phase transition, right? So this is a. So in this theory, right? As so, for example, you probably know this paper by Larry Jaffe and Daisuke, where they looked at perturbative. So they look at weakly coupled n equals 4, even on compact space, but you can unwrap the sphere, right? So in principle, so this point, which corresponds to the loss of thermodynamic stability, right? So it's not necessarily a point of phase transition. So it's it may be a point after which the system just becomes completely unstable, and I mean, this new phase is not known. So it's a bit yeah. So it's a point which where you just lose thermodynamic stability, but it's not necessarily a second order transition point. So a related question is, do you know what happens to sound modes?
Oh, okay, that is very good question. The sound channel is very complicated, and it is in our plan to probe that problem.
Yes. Yeah, because one signature of a second order phase transition would be that the speed of sound vanishes at this point, right? So that's
yes.
So this simple signature. Yeah. Thank you.
Okay, thank you. I think we have to move on. Thank you very much again, Farid, for your talk. Can you stop sharing so that Derek Tini can start sharing his slides? He will talk about hydrodynamics and broken code.